Hello everybody and welcome to our next video in Unit 1, which starts to get us introduced to periodic trends and atomic properties. This video specifically is only going to talk about Coulomb's law, and we're also going to talk about just ionization energy. These two topics tend to take a little bit more time than the last one, so we're going to break this up into two. Anyway, you learned in Chem 1 a little bit about periodic trends, right? So the periodic table is not just a mishmash of elements kind of just thrown together any certain way. There's a reason why every element has its place on the periodic table. And that's a result of periodic trends and periodic law. So there are certain properties that tend to repeat themselves over time. And you might remember talking a little bit about this. I know if you had me, we did a little graphing activity where you were able to see how some of these trends work and why we call the periodic table the periodic table and not just a table of the elements. Specifically in Chem 1, I know I talk about ionization energy, electronegativity, and atomic radius. We did not talk about these last two, but if you could do these top three, then we could do these last two pretty easily. We are going a little bit more in detail with these periodic trends. So it is important to truly understand, and I know I've said this to you a couple of times, within your core, what these trends mean. And in order to do that, there's something that we need to talk about first, and it's a real fundamental idea in all of chemistry. So in order to better understand these properties and their trends, we must discuss a fundamental idea in all of chemistry and in physics, and that's what we know as Coulomb's law. So let's go ahead and get this written down here. This is known as Coulomb's law. And Coulomb's law explains how electrons are held around the nucleus. So you might not have wondered this yet, but maybe you have. What keeps an element together? Right? Why don't electrons just fly into the nucleus? There's a whole bunch of different physics stuff that goes into that more so, but why does the structure of the element look the way that it does? So I'm looking at this isotope of helium right here. Why does it look like that? Let's get into this for a little bit. We know that positives and negatives attract, and we can infer what each of these pieces are. So this is an isotope of helium-4, as you could see down here. So because this is the isotope helium-4, we know, because its atomic number is 2, it's got 2 protons in its nucleus. We know because its mass number is 4, it has 2 neutrons. And we know that it has 2 electrons because this is a neutral element that's listed up here. And ultimately, it doesn't matter which is which, whether these are protons or neutrons, because either way, there's 2 of each of them there. So we don't really have to decipher which is which. We know that positives and negatives attract one another. So what is attracting and repelling in this case? If these blue spheres are your protons, then there is a slight attraction between your protons and your electrons right there. So they are going to attract one another. Now, why don't they totally fly into one another? Like I said, that has a lot more to do with physics than I really want to understand. I am not a physics person. Maybe Mr. Nina knows the answer to that much better than I do. But they attract one another, and that's because they're opposite charges. So what I'm going to do here is I'm going to get a text box, and I'm going to try to color code this as best as I can. Let's go ahead and make this in front of that. So I'm going to do this in pink right here. It's hard to tell that the arrows are pink, but I tried. Your protons, and protons will say in the nucleus, and electrons in the valence shell attract. And that's because they are both positive and negative charges. Like I said, I'm going to color code this, so I can go back and refer to that at some point. Let's make it pink right there. So protons in the nucleus and electrons in the valence shell will attract one another, right? And that's because they're positive and negative charges. However, because I also have two protons that are practically on top of one another, right? In that nucleus, you're going to have a heck of a lot of protons that are within very close proximity to one another. So although these two, your protons and your electrons, attract one another, your protons in the nucleus also repel one another. They're being held together by other forces of attraction, like I said, we're not going to get into, but they are going to repel one another, and they repel each other more strongly, and that's because your protons are closer to one another. That's why I made these green lines bold right here, is because even though my proton and electron attracts each other, that attraction is not as strong as the force of repulsion between these two protons, and that's because the protons are very close to one another. So let's go ahead and color code this here. I'm just going to copy this box and I'm going to put it, do it on this side, it doesn't matter. But your protons in the nucleus repel one another more strongly because they are very close to one another. And this whole idea behind proximity is going to be huge when we talk about Coulomb's law. And let's get this color coded right there. So this brings us to what Coulomb's law means, right? So here is an equation for Coulomb's law below. And this looks very scary, but it's really not, because you don't have to memorize this equation. This is not something that you're going to be calculating with. It's not even on your equation sheet. I don't think it is. You just need to know the idea behind Coulomb's law. So before we talk about the idea behind it, let's talk about what each of these variables mean. We see force right here, this letter F. And this is the magnitude of the force between two charged particles. So we were talking about protons and electrons here. Protons and electrons are charged particles. So what's the force of attraction or repulsion between those two particles? This little thing right here, notice it's not an equal sign. It's just a little bit different. This means proportional. Proportional. So the force of attraction is proportional to, now I have Q1 times Q2, and these Q's are the charges on the particles. So charge on the first particle and charge on the second particle. Because in this case, this example, when your charges are opposite, when I have a positive charge and a negative charge, those are going to attract one another much more readily than two negatives or two positives would. And that's because positives and negatives attract, right? We don't like two negatives together and we don't like two positives. It has to be different charges. And R, which is R squared on the bottom, that's our radius, right? Or the distance between the two particles. How far apart are these particles from one another? What you need to know is right down here in this last section. What does that mean? What does this equation mean? Coulomb's law states that the charges on particles, so the charges on particles and their distance from one another, how far they are, affects their attraction for one another. So the higher charges, or the higher magnitude of charges, we'll say higher magnitude of charges and a closer distance leads to a stronger attraction. This is huge. So let's go ahead and I'm just going to highlight this because it's hard for me to circle on this little tiny pad I have here. This is it. This is Coulomb's law. This is huge. Higher magnitude of charges And the closer those two particles are to one another means that those particles will be more strongly attracted. What does higher magnitude of charges mean, right? What that means, for example, and we're going to get more into this in the next unit, but if I have a +1 and a -1 charge versus a +2 and a -2 charge, these will more strongly attract than the +1 and -1. And that's because they have a higher magnitude of charges. This is Coulomb's law. This is what's going to help us understand all of these periodic trends, right? So like I said, you do not have to memorize that equation with that proportional. Doesn't matter. You need to know what I highlighted right there. I'm going to put up on the AP words to know, or the phrases that pay wall. Coulomb's law is going to be up there. I know we talked about when in doubt, mole it out. There's another one to add to that. If you're talking about some stuff that doesn't involve moles, when in doubt, the answer is probably something to do with Coulomb's law. So anyway, let's use that in order to describe ionization energy, or to talk about ionization energy. So what is ionization energy? You might remember talking about this from Chem 1. If not, that's fine. That's why we're going to define it here too. Your ionization energy, one of our periodic trends, one of our repeating patterns on the periodic table, is the energy that's required to remove one electron from a gaseous element or ion. The energy required to remove an electron. Typically, for ionization energy, this is when you have your element as a gas. So you'll notice here in our equation that's listed, this element X, whatever it may be, is in the gas state of matter. And I am ionizing that. So I am making a charged particle, and more specifically, I'm removing an electron. So notice that I have the removal of that one electron. So let's get our pen back here. I have one electron right here that's been removed. And then I produce a positively charged particle. In this case, I produce a cation. And remember, cations are positively charged. So take away that electron, I have a positively charged ion. This whole entire process requires energy. And the amount of energy it requires is different for all the elements. And it's also different depending on which electron you're taking away from an element, because of course, other than hydrogen, every element has more than one electron. So we're going to look at aluminum in this case. You might recognize that aluminum has 13 electrons. That's its atomic number on the periodic table. So it takes so much energy to remove all 13 of those electrons. You'll notice that there's 4 values listed here. And this is how much energy is required to take away those first 4 electrons. So here I have aluminum as a gas, right? Just elemental aluminum. And I'm removing an electron. This process requires 578 kilojoules per mole of energy. However, because elements have more than just one electron, like we said, you can quantitatively determine this energy for all the continuing electrons. So let's say I want to remove a second electron from aluminum. If I look here, I'm going to take that aluminum +1 and I'm going to remove another electron from that. And in the process, I'm going to produce that electron again. And I have the aluminum ion, but in this case, it has a +2 charge. Not only do your number and types of elements have to be the same, balanced on both sides, your charges have to be balanced as well. So here I have an overall charge of +1. If I have a +2 and I have that negatively charged electron, this gives me an overall charge of +1 as well. This second electron requires 1,820 kilojoules of energy to remove. If I remove a third electron, Here it is. If I have aluminum +2, remove another electron, there's the ionization energy, 2,750 kilojoules per mole. That fourth electron, holy moly, check that out. Look how that ionization energy really got very, very high. I mean, let's see, like more than tripled, almost quadrupled, more than quadrupled, actually. So why did that happen? Right? Why does the ionization energy values have this particular appearance? Why do these ionization energies have these particular values? Right? Maybe not exactly, like, because we can't estimate 1,820, but why does this last ionization energy go up so much? Why does it take so much energy to remove that fourth electron? I have a note down here as well. You'll see how it says I1. A lot of times in textbooks, the first ionization energy is reported. So this I1, is the first one that you would see, like when they list trends in ionization energy, they'll typically list the first one, which a lot of times is abbreviated as I1. So why does aluminum have these particular ionization energies? Why is there such a huge jump between these two? Well, we can describe that because we can look at the orbital notation for aluminum. So we already said that aluminum's got 13 electrons, right? 13 total. Here's its orbital notation. So you could use those, you can count the arrows. There's 13 of them in their respective orbitals. Which one of these electrons is going to be removed first? So which one of these electrons corresponds to that first ionization energy? Well, it's going to have to be this one right here. That outermost electron is going to be removed first. Why is that outermost electron going to be removed first? That's because this electron is the farthest from the nucleus. Far from the nucleus. If you think about aluminum, it's got its nucleus in the middle, it's got its first energy shell, it's got its second energy shell, and then it's got its third energy shell. Those electrons that are in the third energy shell are the farthest from the nucleus. Therefore, that farthest electron is the easiest to remove because that nucleus does not have as strong of a hold on that electron. So it requires the least amount of energy to remove. Its ionization energy is the lowest. Which one of these electrons would correspond to the second ionization energy? Well, that one has to be the next farthest from the nucleus. This would be one of my 3s electrons right there. And in the same vein, what about this third ionization energy? Well, that would have to correspond to this one right here. Now, you might be able to infer, all right, we've been talking this much. So this fourth energy level must, or this fourth ionization energy must correspond to this one right here. But why is that fourth one so much higher? Well, how many valence electrons does aluminum have? Aluminum has 3 valence electrons. And look, here they are. 1, 2, 3. These correspond to your valence electrons. Once we get beyond those valence electrons, these are called your core electrons. And those core electrons are closer to the nucleus. I'll just write closer here. Are closer to the nucleus, and therefore that nucleus has a stronger attraction to them, and then they're harder to take away. So that's why we see such a huge jump in ionization energy, depending on whether or not we're talking about valence electrons or whether we're talking about core electrons. Depending on whatever element you look at, you're going to see a massive jump once you get into your core electrons. Let's look at this thing right here, this little table. So we have going across a period, right? So sodium's in the third energy level. This would be across the third period. Sodium's got 1 valence electron. I'll just put VE. And argon's got 8 VE. Going down like that. So 1 through 8. Notice to remove sodium's first electron requires 496 kilojoules of energy. Look how much is required to remove that next core electron. Goes up significantly. Let's look at magnesium, 2 valence electrons. First electron, a little bit more difficult to remove than sodium's, a little bit higher. But the second one is much easier to remove than the second one for sodium. And that's because magnesium's second electron is a valence electron still. We get that huge jump in energy once we get to that core electrons. Aluminum, look, 578, 1820. This is one we talked about before. Actually, we have that massive jump. And phosphorus, it has 5 valence electrons. Here it is. Boom, boom, going up slowly, going up slowly. Here we go. 6,270 to 22,000. This goes to show that phosphorus has 5 valence electrons because it becomes very difficult to remove one of those core electrons. Inner shell electrons are also called your core electrons right there. And this is the general idea behind ionization energy. It becomes significantly more difficult to remove electrons that are closer to the nucleus, right? Because of Coulomb's law. And we can look at this trend very nicely if we plot ionization energy versus atomic number. So you did this in Chem 1 if you had me, at least. Maybe if you had Mrs. Bartholomew, I'm not sure. But I always have my students plot some trend versus their atomic number. So we have something that looks like this. You'll notice that the D block starts to get a little funny. So I'm going to cross out the D block here. Typically, these trends are only true for your main group elements. So your main group elements would be like your S and P blocks on the periodic table. Notice how all of my alkali metals are at the valleys of this graph. So I have lithium, sodium, potassium, rubidium, and cesium. All of these are alkali metals, whereas all of the top, all of the peaks, helium, neon, argon, krypton, xenon, radon, these are all your noble gases. This beautifully demonstrates what periodic means. We have some trend. It starts off very low at lithium. Trend does whatever it does, goes up till it reaches a high point, and then the trend repeats itself. So even though I'm continuing an atomic number, it's repeating, goes all the way back down, and then the trend repeats, goes to a high point, and then it goes all the way back down and repeats. It's a periodic pattern. It's periodically repeating at one after the other. So while we're on this topic, actually, let's talk about what the group trend is based off of this particular figure that's given to us. We could see as I go down the alkali metals and as I go down the noble gases, we see that our group trend, ionization energy, decreases going down. As I go across a period, so going across a period would be going from lithium to neon, for example. So here is going across a period. We could see that it generally goes up, right? It's not a straight shot going up because there are a couple of anomalies in there, which we're going to talk about. But we're going to say generally increases from left to right. Let's talk about what this means. Why would our group trend decrease going down, and why would our period trend increase generally? Why do we have those anomalies? Let's think about it. As I go down a group, so I have lithium. Lithium has 2 valence shells, right? It has 1 shell around it and it's got 2 shells. So this is 2, I'll put shells. Sodium has 3 shells around it. Potassium's got 4. Rubidium's got 5. And cesium's got 6. So because as I'm going down a group, I'm adding energy shells that are surrounding that nucleus. So I'll do that over here so we could see it. If lithium's got only 2 shells around it, whereas cesium has 1, 2, 3, 4, 5, a lot more shells, right? that nucleus is farther from that outermost shell. And because that nucleus is far from that outermost shell, it's very easy to remove those electrons. It takes less energy to remove cesium's one valence electron because that one valence electron is very far away from the nucleus. This is Coulomb's law, right? An application of Coulomb's law. So trend decreases going down, and that's because your electrons farther from the nucleus require less energy to remove. You might also see, I think in the I do, we do, you do, there's some talk about shielding in there. This is also true, but I don't always like to use that word, the S word, because then everybody uses the S word for everything, right? So not going to use that. I like to say electrons farther from the nucleus require less energy to remove, and that's because of added shells, right? Electrons farther from the nucleus. I'll put in parentheses here because of added shells. There we go. So it's easier to remove this electron because it's farther from the nucleus than it is to remove an innermost electron. And because as I go down a group, I add shells, of course, they get bigger. Generally increases from left to right. So and let's talk about generally first. We'll forget about the anomalies for now. As we go across, I'm going to draw another picture up here so I could see. So let's do from lithium to neon. Here's lithium. It's got 1, 2 shells around it. If beryllium also has 2 shells around it, but that nucleus is stronger, it gains an additional proton. So it's got an additional proton there. That nucleus can pull on that outermost energy shell more because that nucleus is getting stronger. We say that it has a higher nuclear charge. That nucleus is getting stronger, and therefore it has a stronger attraction to that outermost energy shell. The magnitude of the charge is getting higher. If I'm adding protons to that nucleus is becoming stronger, which can shrink the electron because the number of energy shells is not changing. Now, this is generally true because as you see, it's much more difficult, actually, well, not much, just a little bit harder to remove that next electron from beryllium than it is for boron. So why is it harder to remove boron's electron? So why is it easier to remove boron's outermost electron if that shell should technically be shrinking, right? If I'm adding nuclear charge going across, why do I have these 2 little bumps, right? Let's go ahead and put in this period trend here before we get into the anomalies. Generally increases from left to right. We're going to say that adding protons to the nucleus increases nuclear charge, which attracts electrons more strongly, pulls them in closer. Make sure the formatting stays right. There we go. So why? Why do we have these little blips in the graph? Let's take a look at our group 13 elements first. So I'm just going to highlight here. Group 13 would be if I have this element right here, and if I had this element, if I had gallium, and if I had indium. Indium's over here. So why do I see these weird blips in the graph? So let's label this. So I have a group. Let's think about their orbital notation. So I'm going to compare beryllium to boron, right? Beryllium has 2 valence electrons, whereas boron has 3 valence electrons. If I look at their orbital notation, so here's beryllium and here's boron. Beryllium in the 2s sublevel has 2 electrons. Boron, however, I drew that a little bit weird. Let's erase those. Here's 2p, here's 2s. Boron has 3 valence electrons. Because boron has this 1 valence electron that's kind of just hanging out, it's actually easier to remove an electron that's not paired versus an element that has a full pair around them. It's easier to remove this 1p electron because that p subshell, again, is farther away from the nucleus. And also, it's more difficult to take away electrons from totally filled shells because that shell is stable the way that it is. So this p electron's a little bit farther away from the nucleus. Even though it's still in the second shell, those p electrons are a little bit farther away. So it's easier to remove that added p electron. So let's make a little text box here. And we'll say p electron farther from the nucleus than s electrons. And that's why it's easier to take them away. It all has to do with that Coulomb's law. It literally comes back to that just about every single time. Let's talk about our group 16. So group 16 is the other blip in the graph. So I'll use a different color here. Let's use this one. And let's just highlight it. So I have this element, this one, I have this one, and I have this one. Okay, so this is group 16. So group 16 would be like your oxygen, your sulfur, and your selenium. So let's take a look at their electron configuration. I'm going to compare nitrogen and oxygen. So that's this one. Nitrogen's right here. Oxygen's right here. This one's boron. That top one's beryllium. So I have nitrogen. I'm just going to draw its orbital notation. And oxygen. 2s. 2p, and oxygen I have 2s, and I have 2p. 6 valence electrons versus 5 valence electrons. What's the difference? Why is it easier to remove that last valence electron from oxygen than it is to remove the last valence electron from nitrogen? It comes down to this. Let's take a deep dive. Right here. That one. What do we know about electrons? We know that electrons don't like each other. Why don't electrons like each other? What do they have in common? They both have the same charge. Coulomb's law says that opposite charges attract one another. Within this shell, right here, that last valence electron, once I add that next electron, those electrons start to repel one another. And because those electrons repel one another, it's easier to remove that last valence electron. It all comes down to electron repulsions in this case. So I'm going to make another text box. Let's just copy this one because it's going to be a little bit easier that way. Copy, and we'll paste. Oh, not inside. Copy, paste. Bring it right over here. Oh, I guess this was from the previous page. That's fine too. We could say that repulsions within the 2p shell allow the next electron easier to remove. So even though ionization energy tends to increase from left to right, that's why we have these little tiny dips going otherwise. This first one is because that next p electron's just a tiny bit farther from the nucleus. It's easier to remove. And in this case, we add that next electron, which electrons don't like each other, therefore they repel. And it's much easier to remove an electron that's repelled because they want to get farther away to begin with. And here's a nice little image here. So we have to remember that our protons are what attracts one another in the nucleus. Our protons will attract the electrons, like this, but electrons will also repel other electrons. And that's, again, the whole idea behind Coulomb's law. This video is pretty long, so let's go ahead and talk about sample problem 12. The first ionization energy for phosphorus is 1,060 kilojoules per mole, and for sulfur, it is a little bit less than that. It's 1,005 kilojoules. Phosphorus has 5 valence electrons, whereas sulfur's got 6. So a lot of times it does help to draw that orbital notation. So phosphorus is in the 3rd energy shell, as is sulfur. So I'm going to write 3s, 3p, 3s, 3p. Just like we were doing before. 1, 2, 3, 1, 2, 1, 2, 3. Go back and double that guy up. Easier to remove this last electron, right? Which is what we were literally just talking about. Easy to remove this electron here because those electron repulsions become dominant. And when they start to repel, it's going to be easy to remove the electron. Here we go. So let's go ahead and paste this in. It's just easier that way. It is a little bit, I'm on my school computer now. It is a little bit easier to use my school laptop than my home computer. So even though it doesn't look like it is, but I think I just need to practice on this laptop. Anyway, this last electron is easier to remove because the electrons in the 3p shell tend to repel one another. So let's do this last sample problem together, sample problem 13. Which atom has the largest first ionization energy and which one has the second smallest ionization energy? Explain your choices. So I'm just going to number these right here as 1, 2, and 3. So 1, 2, 3. Okay. Largest first ionization energy. We have to consider how many valence electrons these have. 1s2, 2p6. Looks like this guy has 8 valence electrons. So this must be a noble gas, and particularly it must be neon. Next one looks like I have 1 valence electron there. And for number 3, I have 2 valence electrons. So based on how many valence electrons it has, we can identify which one would have the largest first and which would have the largest second. So let's go ahead and start to identify each of these. The largest first ionization energy. The one of those that has the largest first ionization energy would be number 1. So 1 has the largest first ionization energy. Why is that? Because it has a full outer shell, right? And because it has a full outer shell, that atom is stable. And because it has a very high nuclear charge, that nucleus can pull those electrons in much more closely. So there's a couple of reasons you could say for this one. I'm going to list quite a few of them. All the electron clouds are filled, and therefore the element is stable. We can also say this element has a high nuclear charge and can pull the second energy level in closer, making the electrons harder to remove. You're going to see that with AP, you should try to be as concise as you can. I know I always say chemists don't like a lot of words, but you do have to use words to explain, right? So you can't just say like it's higher for this one because of whatever. Be a little more precise. Okay, we want to get the words out of you in order to describe something. Let's say which one of these has the smallest second ionization energy? Which one is it easiest to remove that second electron? Well, I know that it's still going to be pretty difficult to remove the second electron here because I'm still in that valence shell. Removing the second electron from number 2 becomes much more difficult because I'm getting to the core right here. So there's our core electrons. Whereas removing this second electron from number 3, I'm still in that valence shell. So because number 3 is, we're still in that valence shell, we're not quite yet at a core electron, it's going to be easiest to remove the second electron from number 3, thus the ionization energy is lower. So 3 has the smallest second, we'll say, energy. And the reason being, it has 2 valence electrons, which are farther from the nucleus than 1. And valence electrons are easier to remove than core electrons due to proximity to the nucleus. Now I'm being like I feel like I'm being very verbose right here, but you kind of want to be to explain these, and that's so you get your point across. You want the AP readers to know that you understand why, right? So 3 has the smallest ionization energy. It has 2 valence electrons, which are farther from the nucleus than number 1. And the valence electrons are easier to remove than core electrons due to proximity to the nucleus. That would tell any reader that you know what you're talking about. I know this video is very long. I'm sorry. It's kind of just the way it is. Lots of talking for this. We're going to do lots of practice with periodic trends in class. So if you're a little like, what's going on right now? And we have more trends, that's fine. We're going to get it all under control. As always, if you have any questions, please let me know. Talk to me in class, but we're going to do lots of stuff with this in class. We're going to work through it all throughout the year because a lot of these periodic trends you will see as multiple choice questions on the exam. I will see you in the next video, which is all about maining for trends, and I'll see you then. Bye.